Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to give a complete classification of all the finite subgroups of SO3. And in doing so, what we will also do is classify the Platonic solids. Now, this classification is extremely important in mathematics, not only because it tells us a lot about the rotational symmetry inside R3, but this classification rather amazingly appears all over mathematics, from the study of Kleinian singularities in algebraic geometry to Lie theory. And that's one of the reasons why it's important to have a look at this in as many settings as possible. Okay, so let's look at our setup that we have. So we're going to start with some group G, which is a finite subgroup of SO3, the rotations inside three-dimensional space. And what we can do is we can attach to that the set of poles. Okay, so if you have some group like this, you've got lots of rotations. So the rotations will all act on the unit sphere, and each rotation will be about some axis, so we'll have two poles. So for each non-trivial rotation we have in here, we'll get two poles, and as we run over all the group elements, we'll get a whole set of poles x. And one of the things that we saw in the previous video is that the set of these poles is actually a G set, so G acts on them. So if you rotate by some element of the group here, it will send one of the poles to another pole. Okay, so being a G set, you have an orbit decomposition, and we can write out the orbit decomposition like this. Suppose R is the number of orbits, so the orbits go from G dot x1 up to G dot xr, and here you have a decomposition into a disjoint union. So in this classification, what will be very important are the stabilizers of elements. Okay, so the stabilizer of xi, the order of that we'll denote by EI. So what we want is actually the stabilizers of all the elements inside X, or all the poles, but the stabilizer of G dot xi, remember, it's just a conjugate of the stabilizer of xi. So these two stabilizers have the same order. Okay, so we'll denote that by EI. So this EI is constant on each of the orbits. Okay, so there are basically R of these EIs that you have to contend with. What we'll do is that these orbits, I guess you could have put them in any order. So we'll reorder them so that the E1 is the smallest, E2 is the next smallest, and so forth. So these are in ascending order, although some of them may be the same. Okay, so let's just give a little example so that you remember what happens. So a typical sort of finite subgroup of SO3 is the rotational symmetry group of some Platonic solid like this cube here. Okay, so suppose GP is the rotational symmetry group of the Platonic solid P. That's the notation that we'll use. And let's have a look at one of these orbits. So remember, the orbits here correspond to what? The orbits of X correspond to the faces, the edges, and the vertices. Okay, so for the edges, what happens here? So remember, all the edges, you can rotate any edge to any other one, which means the poles are also forming one orbit, so the corresponding poles. So how does that work? Okay, so for example, if you have edges like this one here, you can look at the axes which go through the middle points of those edges, and you can rotate. Right? So in this case, you have a rotation which, because it's an edge, you have to send this edge rotated back to itself. You must rotate by 180 degrees. Okay, so if you want to do such a rotation, of course, okay, which rotations fix that edge, okay, then the only possibilities is you rotate by 180 degrees like that. So it turns out that the stabilizer of those two poles, okay, the stabilizer of these two poles, which are the midpoints of these edges, that means that you must have rotations which go through those, has an axis which goes through those midpoints of those edges, and the only possibility is you rotate by 180 degrees. So there's a rotation by 0 or 180 degrees. So the stabilizer there has two elements. Okay, the one rotation by 0 and the other rotation by 180 degrees. So EI equals 2. So the orbit corresponding to the edges, when you're looking at the rotational symmetry group of a Platonic solid, that EI corresponds to 2. And that's one way to mark out the edges. Remember, there's a duality between the vertices and the faces. So of course, from the group, you can't distinguish faces from vertices, but the edges will be marked out by the fact that this I equals 2. Okay, so let's have a little look at some basic facts concerning our data that we have here. Okay, so the first one, EI is the order of some subgroup the stabilizer of xi, some subgroup of g. So Lagrange's theorem tells you that EI divides the order of g. Okay, EI divides the order of g. So that puts a maximum limit on this EI. Okay, and that's good information to know. The other quantity that will be extremely important is not only these EIs, one thing that will crop up a lot is this expression, this function of EI, 1 minus 1 on EI. Okay, so let's see what happens as you increase this EI, the order of the stabilizer group. If this shoots off to some very large number, at most you can be subtracting 1 on going towards infinity. You're going towards 0 here. So the biggest this can be is 1, and it can't equal 1. Let's suppose instead we shrink this EI to as small as it can be. Now remember, this EI has to be the stabilizer group of one of these poles, and being a pole means that this can't be 1, right? Remember, the G set of poles are basically the poles corresponding to some non-trivial rotation. Okay, so that non-trivial rotation will live inside the stabilizer group, so that means that this will contain both that non-trivial rotation and 1, so this is at least 2. So EI is at least 2. So that means that if you want to subtract a bigger and bigger thing, you can subtract all the way down to 1 on 2. So 1 minus half gives you half. That's the most that you can subtract, and that occurs when EI equals 2. Okay, so this expression here is sandwiched between half, can equal it, up to 1, but it can't equal 1. Okay, so what's our aim here? Our aim here is to try to classify all these finite subgroups of SO3, and we want to classify them not just up to isomorphism, but actually up to conjugacy, okay? Which just means change of coordinates, okay? Because when we're looking in SO3, of course, remember, we like to look at things up to symmetry only, okay? So for example, one possibility is the rotational symmetry group of a Platonic solid, okay, like this cube here. But of course, the way you put the cube inside R3, okay, if you put it in slightly differently inside R3, you'll get a different subgroup of SO3, okay? But the point is that the different way if you rotate it a certain way, it will conjugate the original matrix or the original subgroup by that rotation. So the ways of changing that subgroup is by conjugation. So that's what I mean by up to conjugacy here, okay? So when we say the rotational symmetry group of a Platonic solid, actually there are lots of such rotational symmetry groups as subgroups of SO3, okay? And they correspond to how you want to think of the Platonic solid sitting inside R3. Okay, well, let's give the theorem which tells you what the possibilities are. And it's an absolutely beautiful theorem. Okay, G has to be one of the following 5 possibilities. And the way I'll list them down is using the usual notation from Lie theory. Okay, so the classification I'll simply lay it in Venn diagrams. So the usual letters are A, D, and E. Okay, A is an infinite family, D is an infinite family, and E is a finite family consisting of E6, E7, and E8. It's a little bit funny, the notation here, and that comes from Lie theory. There are B's and C's and F's and G's as well, so, but they do not occur in this part. Okay, so let's look at A firstly. Okay, so A corresponds to a cyclic group of rotations about a fixed axis L. So let's suppose you've got a vertical axis and you just rotate around like this. Okay, they're the only rotations that you have inside G. Okay, and you can rotate by 1/n of a revolution. Okay, and let that generate a group. So all multiples of that. And if you look at all multiples of that, you're basically rotating by some integer multiple of an nth of a revolution. Okay, so if you look at the set of them, there'll be n of them. Okay, and that will be some finite subgroup. Okay, finite subgroup of rotations. Okay, and one way to think of that is that, well, instead of looking at it in 3D, you can look at it in terms of, well, what's the rotations of some regular n-gon, okay? If you think of this as inside the plane, okay? You can rotate, for example, a regular hexagon, 6-gon. The way you can rotate that is you can send one edge to any other. So there'll be n of them in a regular n-gon. So here there'll be 6 of them. And you can rotate by what types of angles. There'll be 1/n of a revolution or any integer multiple of that, okay? So that gives you what you have here. Okay, so in this case, there's one axis of revolution. Okay, so if the vertical axis, you're just revolving like this, okay? You're revolving like this, one axis of revolution, okay? So that means that there are only 2 poles, okay? And these 2 poles, if you try to let this group act on it, they are in distinct orbits. This pole here doesn't get sent to this pole here because the only rotations fix both of them. Okay, so there are two orbits. So the cardinality of x mod g is 2. Okay, and what are the stabilizers of these 2 points? Well, every rotation, all the rotations are about this axis, so the whole group stabilizes it. So E1 equals E2 equals the order of g. Okay. So the next example here is type D, which is the dihedral group. Okay, and so dihedral group you normally think of as the symmetry group of a regular n-gon. But here I want to think of this as the rotational symmetry group of a regular n-gon in R3. So what I want to do is I want to think of some regular n-gon like this hexagon here. And rather than thinking of it as inside the plane and looking at the symmetries of that, I want to think of it inside 3 space, and I want to think of it as a degenerate Platonic solid, okay? A very degenerate one, where basically there's a top face, which is like this one, and a bottom face, which kind of coincide, but we'll think of them as 2 faces. And then there'll be edges and vertices, which are the usual edges and vertices of this regular n-gon, okay? And we'll think of the rotational symmetry group of that, okay? And of course, it will turn out to be just the usual dihedral group, okay? So firstly, you can look at axes which go through the midpoints of the face, okay? And so there'll be the usual rotations that you see of this regular n-gon. And there'll be n of them, okay? That's the corresponding to n here. So that's that cyclic group of rotations. That's going to be the stabilizer of these 2 poles, okay? And then what do you have? What other rotations do you have? Well, you can look at axes which go through either vertices and or midpoints of edges. So here maybe you have 2 pair of midpoints of edges, and you can look at rotations of that. Okay, so here you can only rotate by 180 degrees. Okay, so that's a reflection in the usual dihedral group if you think of this in the plane. But if you think of this in R3, it's a rotation like that, okay? And it's a rotation where the axis is in the same plane as the plane of the regular n-gon. And of course, you can only rotate by 180 degrees, so that's the stabilizer group of the poles which correspond to, in this case, these opposite edges. So that you get a 2 here. And you can do something similar with the vertices. You can, here you've got an axis which goes through opposite vertices, and you can rotate by 180 degrees. And that's the stabilizer of the poles at these vertices. So here, this is that regular 6-gon, okay? So since 6 is even, if you have an axis, it goes through either both vertices or both midpoints of edges. But if you have n is odd, like a pentagon, then you'll find that every axis of reflection goes through a vertex and the midpoint of an edge, okay? So, n can be even or odd here, and this gives you the dihedral group, and it also tells you how you get a subgroup of SO3 by thinking of it as a rotational symmetry group of regular n-gons in R3. So you think of this as a rather degenerate Platonic solid. And the last 3 possibilities we've seen before. So remember, the Platonic solids come in dual pairs. So the cube is dual to the octahedron, the dodecahedron is dual to the icosahedron, the tetrahedron is self-dual. And we saw that the rotational symmetry groups of the cube and the octahedron are the same, and similarly the rotational symmetry groups of the dodecahedron and the icosahedron are the same. And there's only 3 other possibilities than the infinite families that you find in types A and types D. Let's have a little bit of a closer look at these 3 rotational symmetry groups of Platonic solids. We call them E6, E7, E8. They're the types that you have. Now remember, the number of orbits that you have in this G set of poles is 3. Okay, they correspond to the faces, the edges, and the vertices. Okay, so you'll get E1, E2, and E3. And what are the possibilities for these numbers? Okay, they actually distinguish what happens here. Okay, so the edges, we always get 2. So that's the first 2 here. Okay, and even in this case here, you can think of it the degenerate case where this is, corresponds to 2. In this type D case, you have a 2 for the next number. So remember, these are in ascending order. So it turns out that the only other possibility is if the first one corresponds to the edges, you get 2. The next one has to be a 3. And it's the third order of the stabilizer group, this E3, which distinguishes these 3 cases. Okay, E3 can be either 3, so it has to be at least the middle one, 3, because these are ascending, so it's at least 3. But it turns out it can't be more than 5. Okay, so it can be either 3, that's the case where you have the rotational symmetry group of the tetrahedron. E3 can be 4 when you have the rotational symmetry group of the cube or the octahedron. And also it can be 5 when you have the rotational symmetry group of the dodecahedron and the icosahedron. So this is the beautiful theorem that classifies all finite subgroups of SO3. And what I want to do is I want to actually sketch the proof of this. And the way we'll do this is as follows. Okay, the way we'll do this is firstly, we'll do the numerical part of this, which is the information encoded in these EIs. So here we want to show firstly that there are at most 3 orbits. So there's either 2 orbits in this type A case or 3 orbits in these cases here. And then we want to show that in these cases, if you have 3 orbits, the possibilities for these triples, these are called Platonic triples, are the ones given here. So it's either 2, 2n, or 2, 3, 3, 2, 3, 4, or 2, 3, 5. Once we have that, what do we need to do? We need to say that given this numerical data, we can actually construct the group. And I'll do that in a specific example. What I essentially want to do is, for example, if you're given that you have the set of poles has these properties where you have 3 orbits, and E1, E2, E3 is 2, 3, 4, we're going to construct the cube and the octahedron out of that and show that the group has to coincide with the rotational symmetry group of either the cube or the octahedron. Okay, so now let's sketch the proof of this wonderful classification of finite subgroups of SO3. And the first step here is to classify the possibilities for the EI. Okay, so these EIs, there were R of them, where R is the number of orbits, so we want to say that there are either 2 or 3 orbits, and then the EIs were one of the ones that were listed down in that theorem. Okay, so the way we'll do that is we'll use Burnside's theorem, which tells you what the number of orbits is. So we denoted that by a little r here. And the formula was that it's just the average size of the fixed points that we see here. Okay, so let's have a look at all these fixed points. And this breaks up into 2 possibilities, actually. There's the trivial rotation, which is the identity map, so x1. And then there are all the other rotations that you can possibly have. So we break it up into some like this. And the reason why we do that is actually when you have a non-trivial rotation, its fixed point set is actually quite easy to work out what that is. Okay, so this number can be computed. If you have a rotation, of course, you'll have 2 corresponding poles which correspond to that rotation. It's a non-trivial rotation here. Okay, you'll have 2 poles. And then what else do you have? Well, every other point, other than those 2 poles, every other point in the sphere actually gets moved, so it's not fixed. So it's going to be 2. Okay, the size of this fixed point set is 2. For every rotation which is not trivial, every non-trivial rotation. So you'll get 2 times, for this sum here, 2 times the number of elements here, so that's the order of G minus 1. This here, what's fixed by the identity rotation, or just the identity map? Of course, it's the whole set of poles. Okay, so it's all of X. Okay, so let's rewrite this, okay, on this next line here. Here we've just expanded 2 times the order of G minus 2. And this here, what we can do is we can decompose this into orbits. Okay, so the orbits were g dot xi as I runs from 1 to r. So the cardinality of this is just the sum of the cardinalities of those orbits. Okay, and finally, let's reduce this to information involving these EIs that I introduced here. Okay, so this part here, I've just divided by the order of G, so cancels with this to give you 2, and then you have minus 2 divided by the order of G here. And what about this part here? Well, what is g dot xi? So the key point to remember is that this is isomorphic to the G set G mod stabilizer of xi. And the cardinality of this is just the order of G, that will cancel with this order of G here, divided by the order of the stabilizer. And the order of the stabilizer that you're dividing by is just EI, so you divide it 1 by EI. So this is just a sum from I equals 1 up to R of 1 on EI for this sum here. Okay, and the form that I want to use of this equation is the following one here. I want to bring this term to the left-hand side, and I want to think of this R as a sum from I equals 1 up to R of 1, so you're summing 1 R times, and you're subtracting this from that. So it's the sum from I equals 1 up to R of this 1 minus 1 on EI, and it equals this term here, 2 minus 2 on the order of G. Okay, so here's an equation, and these EIs and this order of G, they're various integers which satisfy certain relations that I told you before. And I claim that because of those relations, the only solutions to this equation here are the following ones. Firstly, R can either be 2 or 3, just as in the statement of the theorem that I gave you. If R equals 2, then you have an E1 and E2. And in this case, what do they have to be? They're just the orders of the group. Okay, they're both equal and equal to the order of the group. If R equals 3, then you'll have an E1, E2, and E3. And you'll have 4 possibilities. They correspond to the types D, E6, E7, and E8. Okay, so the type D was 2 to N, the rotational symmetry group of the regular n-gon, when you think of it as a degenerate Platonic solid. Then 2, 3, 3, E6 correspond to the rotational symmetry group of the tetrahedron. The rotational symmetry group of the octahedron and cube corresponds to 2, 3, 4, and 2, 3, 5 is the rotational symmetry group of the dodecahedron and icosahedron. So type D, type E6, type E7, and type E8. Okay, so at least numerically, this will complete the classification. Okay, so let's see why this lemma is true. And the calculation is rather pretty, and it shows you why you get such an interesting list. And it's kind of the key reason why this classification also appears in all sorts of places in mathematics. Okay, let's see how this works. Okay, so first thing is to work on the number of orbits that you have. Okay, so let's look at the left-hand side. This quantity here, remember, in the fact that I gave you before, this quantity here is bounded below by 1 minus half. So this is smallest when EI is 2, the smallest it can be. So 1 minus half is half. So this is equal to R on 2. But the right-hand side is at most 2. Okay, this is bounded by 2 above. So once R gets to 4, you'll have at least 4 halves, so at least 2 here, so you can't get equality. So the only possibilities are that R is less than or equal to 3. That's the biggest that you can have. Of course, the other thing you might check is, well, can you have 1? If you have 1, well, you just have one of these terms, which is less than 1. And what do you have over here? Well, the order of G is at least 1. So when you divide by that, so we'll eliminate here the trivial group. Trivial group, I guess we've already covered. So if you remove that, then this is at least 2. So you'll have 2 minus 1 is the most that you can subtract. So that means that you can't get equality. Okay, in this case here with R equals 1. Okay, so R equals 1 is not allowed. So that means the only possibilities are R equals 2 or 3. Okay, so that's great. Just by using this equation and thinking about some of the possibilities, you've eliminated everything except for the case where R equals 2 or 3. Let's go through them individually. R equals 2 is easier. Okay, so here you have the sum of 2 things. R equals 2 things. So it's 1 minus 1 on E1 and 1 minus 1 on E2. And it equals this term here. We'll pull out the 2. So this is 1 minus 1 on order of G. 2 times 1 minus 1 on order of G. And the reason why I wrote it this way is when you look at this, right, this type of function appears 3 times. It's a 1 minus 1 on something. Okay, 1 minus 1 on E1, 1 minus 1 on E2, and there's a 1 minus 1 on the order of G. Now, as a function of this E1, this thing here, it's an increasing function. Okay. So this is an increasing function of E1, of E2 here, and of the order of G. And also the E1 and the E2, they're orders of stabilizer groups, okay, which are subgroups of G. So these EIs, recall, divide the order of G. So to get the sum of these two equal to twice this one here, right, you need to make these as big as possible. So E1 has to equal to the order of G, and E2 has to equal to the order of G as well. And the sum of these will be, they'll be the same. So twice this one here, and it'll be 1 minus, since it's the order of G, the order of G. Okay, that's the only way you can get these to be big enough to equal that. Okay, so that's the only possibility. So if R equals 2 indeed, we have E1 equals E2 equals the order of G. And that's what we stated here. Okay, so let's look at the next possibility, which is R equals 3. And in this case, remember, we want to say it corresponds to either the rotational symmetry group of a Platonic solid or the degenerate Platonic solid, which is a regular n-gon, which we sit inside R3, and we think of it as having a face which is in the plane of the regular n-gon. Okay, so the first thing we want to say is that you have a number corresponding to the edges, so there's a 2 at the beginning. So that's the first thing that we want to check. Is it true that the smallest EI is 2? Okay, so remember these are in ascending order. So is E1 equal to 2? Well, let's suppose E1 is greater than or equal to 3. Okay, so to get a contradiction to that, I need to work on this equation a little bit more in a more manageable form. Okay. By the way, these numbers are called the Platonic triples. And the way I'll get these Platonic triples is by rearranging this equation. Okay, so r equals 3 here. So you're summing 1 3 times, so you get the 3 here. And then you're subtracting these three quantities, one on E1, one on E2, and one on E3. And the right-hand side is just 2 minus 2 divided by the order of G. 2 minus 2 divided by the order of G. Now we can rearrange this as some information about the sum of these reciprocals. 1 on E1 plus 1 on E2 plus 1 on E3. Put that to the other side. And then this we bring to the left-hand side. So the 2 minus 2 from the 3 gives you the 1. And then you add a little bit. Okay, whatever that is. So it's at least 1. The sum of reciprocals is at least 1. And this inequality is a very important inequality. And the E1, E2, E3 corresponding to the solutions to this, where they're at least equal to 2, those integers, are what's called the Platonic triples. Okay? I want to say the set of solutions to them, to that inequality, are precisely the 4 possibilities here. Okay, so this infinite family, or these 3 individual things here. Okay, let's see how that's the case. Okay, let's suppose E1 is at least 3. Okay, so let's see how big this can be. Okay, so it has to be at least 1. Let's see how big it can be if E1 is at least 3. So since it's at least 3, I guess the biggest this can be, since you're taking the reciprocals, the first one is at most a third. Okay, if this E1 was 4, it would be a quarter, which is smaller, and if it was 5, it's a fifth, which is even smaller, and it goes towards 0. Okay, so the biggest it can be is a third. Now E2 is also at least E1, because these are in ascending order, so E2 is at least 3, so that this term is at least at most 1/3, and the last one similarly is at most 1/3, so the sum of these 3 is at most 1, which isn't big enough. So that tells you straight away that E1 can't equal 3. Of course, E1 is at least 2, so that means E1 actually equals 2. So that's great. Using this inequality here, we see straight away that the smallest of these integers, orders of stabilizer groups, these EIs, is 2. And that's the number that corresponds to the edges. Okay, great. So what about the next number? So the next number that you see here is either 2, in which case the last thing can be anything, or 3. Okay? So let's see why you can't get E2 4 or bigger. Okay, so let's see what happens to the left-hand side of this. This is sum of reciprocals if E2 is actually at least 4. So E1 is 2, so you have a half here. E2 is at least 4, so the biggest this can be is a quarter. And since E3 is also at least 4, the biggest that 1 on E3 is also a quarter. But when you add half to these two quarters, you get 1 again, which isn't big enough to make it strictly bigger than 1. So that means that this E2 at least 4 can never happen. So E2 equals 2 or 3. They're the possibilities here. Now it turns out if E2 equals 2 as well, you'll get a half plus a half, half plus a half, and you add the 1 on E3. Doesn't matter how big this E3 is, you'll get at least 1. So these are all possibilities. Okay, that will certainly always give you a possibility. So the thing to rule out now is what happens with E3. Okay, so we're going to when E2 equals 3. So we'll assume now that E2 equals 3, and E3 we want to say is what? It's bounded by what? The biggest one you have here is 5. So you want to say it's not 6 or bigger. So let's suppose E3 is greater than or equal to 6. And let's do the same thing that we've done before. Okay, let's look at the left-hand side. So E1 equals 2, so you get half here. E2 equals 3, so you get a third here. And E3 is at least 6, so you get at most 1/6 here. You add a half to a third, you get 5/6 plus 1/6 is 6/6, so that's 1. And again, we see that it's not big enough, so that means that E3 has to equal, well, it's at least this E2 equals 3, so it has to equal 3, 4, or 5. So we do finally see that the only possibilities for these orders of stabilizer groups is given by these Platonic triples here, or this pair here. Now we want to finish the proof of the classification theorem, and that proceeds case by case. So you have to look at types A, D, and E separately. But they all follow a fairly similar formula. So if I show one example, you should be able to show all the others as well. So the key idea here is that we want to essentially construct the Platonic solid, at least in types D and E. Okay, so let's do the example where the Platonic triple we have, E1, E2, E3, is 2, 3, and 4. what I want to show is that if we look at the G orbit of x3, which has corresponding stabilizer of order E3 equals 4, then that gives you the vertices of an octahedron. Okay, so what are the vertices of octahedron? Okay, so I guess there's it's the same as the dual of the cube. So you've got the top and the bottom, the midpoints of the top and the bottom, and then you have the four sides, the midpoints of the four sides. So you have one on the top and one on the bottom, and then 4 in the middle. Okay, so that's what you want to show, that you get the vertices of an octahedron here. Okay, so once you know that this G dot x3 are the vertices of the octahedron, why does it tell you what you need to know? So firstly, G dot x3 is a G set. Okay, so in other words, when you apply the rotations which are inside G, okay, it will send elements of here. So if we've shown there the vertices of octahedron, it will send the vertices of octahedron back to the vertices of the octahedron. And hence it will rotate the whole octahedron back to itself. So in other words, these are just rotations which are in the rotational symmetry group of the octahedron. So you will at least know that the G is a subgroup of this rotational symmetry group. And then to show actual equality, what do you need to do? All you need to do then is to show that the orders of these two groups are the same. Okay, so you just need to show the order of G equals the order of the rotational symmetry group of the octahedron. Okay, so let's start by looking at the question of what is the order of this group G. So what are orders of the group G? And also you want to get an octahedron here. So the vertices of the octahedron, how many of them are there? There are 6. So let's also look and see what the cardinality of this G orbit of x3 is. Okay, so what I want to do is I want to look at that star, that equation that we had, which relates to the order of the group G to all these stabilizers here. So we can just solve for the order of G here. Okay, so let's do that. So you have the sum of these 1 minus 1 on EIs. So the EIs are 2, 3, and 4. So 1 minus half is a half. 1 minus a third is 2/3. And 1 minus a quarter is 3/4. And you sum them up to get you 2 minus 2 on the order of G. So I guess the common denominator here is 12. You get multiplied by 3, 9 twelfths. 9 twelfths plus 8 twelfths is 17 twelfths. 17 twelfths plus 6 twelfths is 23 twelfths. 23 twelfths is the sum on the left-hand side. And let's solve now for this order of G. So I guess 24 twelfths is 2. So this is 24 twelfths, which is 2 minus 1 12th. So this 1 12th is this term here, which tells you that the order of G is equal to 24. This is 1 12th, which is 2 on 24. So the order of G is 24. And of course, we also know that the order of the rotational symmetry group of the octahedron, okay, which has 8 triangular faces, 8 times 3 is 24. So these are, in fact, the same, as long as we can show that G dot x3, this G orbit of x3, are just the vertices of an octahedron. Okay, so let's do that. And that requires a little bit of thought, okay? So what we're going to do is we're going to look at the stabilizer of x3. So let's rotate so that x3 is up the top here, okay? And look at the stabilizer of this x3. So all the rotations which inside this G, which fix this x3, okay? So of course there are rotations which are about the axis through x3 and minus x3, okay? And since G acts on this G dot x3, so does the subgroup, okay? This is closed under, so to speak, actions by group elements in G. So in particular, they're closed under group actions by elements in the subgroup H, which is just the rotations inside G about this x3 and minus x3 axis. Okay, so what are H? Firstly, okay, so you're looking at these rotations, okay? So you're rotating about this axis, and what is the order of this stabilizer group? It's 4. Okay, so you've got an order group, 4 group of rotation. So the only thing you can do is rotate by 90 degrees. Okay, so H, let's say, is rotation by 90 degrees one way. And of course, the square will be in there, which is rotation by 180 degrees. And then H cubed is rotation by 270 degrees or minus 90 degrees. And when you get to H to the 4th, you get the identity rotation by 360 degrees. Okay, so they're the possibilities for what you have. Okay, so the stabilizer of x3, this is a group of rotations about the x3 minus x3 axis, and it's just a cyclic group 1h, h squared, h cubed, where h is just rotation by 90 degrees. Okay, great. Okay, so let's look at the h action on the G orbit of x3. So we've got x3 is in the G orbit, right? G dot x3 is the orbit containing x3. but it might contain another element like this G dot x3 here. And what are the H orbits? So you want to look at these 4 rotations and let it act on the elements inside here. Okay, so x3 of course is fixed. Minus x3 at the moment we don't know whether it's in this G dot x3. It's certainly a pole, but is it inside here? That's not clear as yet. Okay, but if it were inside here, I guess it would be fixed. It will be its own orbit. Any other point on the sphere, like this G dot x3 here, let's see what happens as H acts on that. Well, it's rotating by 90 degrees about this x3 minus x3 axis. So when you apply H, you might end up, for example, here. Here's H, G dot x3. When you rotate by another 90 degrees, you'll get over to the other side, H squared G dot x3. And when you rotate by another 90 degrees, you get back here, H cubed G dot x3. Okay, so if you're not x3 or minus x3, the orbits, the H orbits, will have 4 points, 4 distinct points. Okay. Okay, so what do we know about this G dot x3, this G orbit? The G orbit we saw, okay, here, it has 6 elements. So why was that true? I guess I missed this bit here. So remember, G dot x3, it's isomorphic to G modulo the stabilizer of x3. Okay, so the order of this is the order of G, which is 24, divided by the stabilizer of x3, and that has order E3, which is 4. So that's 24 divided by 4 is 6. Okay, so there are 6 elements inside here, and we break it up into H orbits. One of the H orbits is x3, because x3 is in there. Okay, and what are the possibilities? Any other orbit is either has 4 points, or is the singleton minus x3. Okay, and the only way you can add up to 6 is if you have one H orbit of 4 points, like this, and that gives you 1 plus 4, that's 5 elements inside here already, so the 6th one must be minus x3. So minus x3 must be inside G dot x3 as a result. Okay, that's rather interesting. Okay, so H orbits are x3, it's one of them, minus x3 is another one, and then there's an orbit of 4 distinct points. Okay, so that's what you see here, G dot x3, hg dot x3, h squared g dot x3, and h cubed g dot x3. Okay, great. Well, it's starting to look a little bit like the vertices of an octahedron, right? Okay, but what do we want? We really want this circle here, okay, the plane which contains the g dot x3, to be on the equator. And then there's the symmetry, and we see that this would be indeed the vertices of an octahedron. So why is that true? Well, this argument, you can pick any point inside g dot x3. You could put g dot x3 as one of them. Okay, you could start it with this one here. And of course, what's the stabilizer of this? It's just conjugate to a stabilizer of this. You go through the same argument, and what's part of the point of this argument is that, well, if we saw that x3 is inside this g orbit, then minus x3 is also in the g orbit. So if you repeat this argument with g dot x3, you will find that minus g dot x3 is also in the orbit. Okay, but the orbit, so it's in the g orbit, okay, of x3. Okay, minus g dot x3 is in the g orbit. But what was the g orbit of x3? It was these 6 points, x3 minus x3, and these 4 here. So this minus g dot x3 has to equal one of these 6 points. Well, it's not equal to minus x3, okay, and it's not equal to plus x3, so to be equal to one of them, what must you have? You must have that this equator, this h orbit here, h dot g dot x3, has to lie on the equator. And once you have that, you can see that indeed that these are the vertices of an octahedron. Okay, so that's the conclusion. G dot x3 is indeed this set of vertices of an octahedron. And then we argue that G certainly sends vertices of, rotates vertices of the octahedron back to itself. So it in particular rotates the octahedron back to itself. And since it also has the same number of elements as the rotational symmetry group of the octahedron, we find that it's actually equal to the rotational symmetry group of the octahedron. And in this way, arguing by similar analysis, you can show all the other cases, the E6 case, E8 case, the type D case, and similarly also the type A case. You can show that the only possible finite subgroups of SO3 you can have are those in those types A, D, and E cases. I hope you enjoyed this adventure in pure mathematics.